Hello, I want to work through essentially all of the carboxylic acid derivative chapter in just one big overview. I want to first give you an overview of what the reactions are and then work through the mechanisms. So let's get to it. All right, so with our reactions of carboxylic acid derivatives, that's going to enable us to make acid chlorides, acids, amides, esters. And so we have essentially three big categories of reactions that we're going to focus on. First is synthesis of acid chlorides. There's one way to make an acid chloride. You start with a carboxylic acid and you add thionyl chloride. SOCl2 is thionyl chloride. Thionyl chloride. And that will generate an acid chloride. Acid chlorides are very versatile. They enable you to make any other carboxylic acid derivative. You can make an amide, an ester, you can make a carboxylic acid, which is kind of silly because you just had a carboxylic acid, but they're very useful if you want to make amides and esters. Right, so here, if you have your acid chloride, you can make an amide or an ester. For us, it's probably going to be the best way for us to make an amide. All right, and then you can also make an ester. It's important to note in this reaction that you must have a base. We'll see when we go through the mechanism in a minute that it's critical to have the base there because the base will neutralize the HCl formed in the reaction. If you don't have a base to neutralize the HCl, it can wreck your reaction, can react with other things in your molecule, or it can shut down the reaction because it's protonating things you need to react. Another very popular way to make an ester is the Fischer esterification, and in this case you don't need an acid chloride. You could start right with a carboxylic acid, react that with catalytic acid and an alcohol, and you can make an ester directly. So we have two ways to make an ester, either from an acid chloride or from a carboxylic acid. One way to make an amide, one way to make an acid chloride. And it turns out we have a bunch of ways to make a carboxylic acid because you can start with any carboxylic acid derivative. Again, carboxylic acid derivative, 3 bonds to electronegative elements, right? So here, 2 to oxygen, 1 to chlorine, 3 to oxygen, 2 to oxygen, 1 to nitrogen, 3 to nitrogen. Always 3 bonds to electronegative elements. You can treat this with base or with acid, right? So sodium hydroxide in water or hydronium in water, and that's going to give you a carboxylic acid, right? So that is a summary of the entire carboxylic acid derivative chapter, right? It's just how do you take things that have 3 bonds to electronegative elements and interconvert them, right? And I think the linchpin for all this is the carboxylic acid, because you can turn anything into a carboxylic acid, and a carboxylic acid is the only thing you can turn into an acid chloride, which then you can turn into an amide or an ester, okay? So what I want to do now is work through the mechanisms of these reactions. So I'm just going to go through them one at a time, just so that you have a record of what the mechanisms look like, right? So I'm going to erase the bottom part. We'll go through the thionyl chloride reaction first, and then we'll work our way through the other ones. So the thionyl chloride mechanism is the weirdest one of all this bunch. The other ones are going to look very similar to things that we've done before and similar to each other. Thionyl chloride is different because thionyl chloride is a reagent we haven't met before. Right? So thionyl chloride looks like that. So the sulfur is very delta plus because it has 4 bonds to electronegative elements. So that's going to be very electrophilic. And so we can have a nucleophilic oxygen add to the sulfur, right? And so that's going to give us an intermediate, sorry about that looks like this. It's also important to note here that sulfur has an expanded octet, right? So it has 4 bonds and a lone pair, right? So what happens here, this is going to look a lot like carbonyl chemistry, is sulfur oxygen double bond, much like a carbon oxygen double bond. You can reform the sulfur oxygen double bond and you have a leaving group on here. So that gets us to and we know that chloride is not a very good base, right? HCl is a really strong acid. That means that Cl- is not a very good base. And so Cl is going to act instead as a nucleophile, and it's going to add to the carbonyl. And that whole group with the positively charged oxygen and the sulfur and the chlorine is going to act as a leaving group for us to reform the carbonyl. And that's how we get to the acid chloride, right? And then that generates that as the other byproduct. That's going to break down to form HCl and SO2 gas. You don't really need to worry too much about it. Just for completeness sake, it's important to know that. But the key for us is that thionyl chloride makes the OH into a good leaving group. Cl- acts as a nucleophile to make a tetrahedral intermediate where we can have the oxygen part leave, and that leaves behind the chlorine on the acid chloride. Okay, again, bit of a funky mechanism, different reagents than we've seen before, right? But now, if we have that acid chloride, right, let's look at how that is going to react. All right, so let's do our synthesis of amides, right? So if we react an acid chloride with an amine, right, so let's take ethylamine, right? And when we do these reactions, again, we often have another base in there. The most common base is pyridine. This is called pyridine, right? And we'll see how pyridine is going to react to prevent the formation of HCl. Okay, so the ethylamine is going to react to give us a tetrahedral intermediate. And like we've seen in reactions of acid chlorides before, there's always going to be a good leaving group because the chlorine is there. So you can reform the carbonyl. Cl- is going to leave. And then to get to our neutral product, we need to deprotonate, and that's why we have pyridine around, so that we can deprotonate. So that's going to give us our amide plus pyridinium, right? And again, it's better to have pyridinium chloride than having HCl, because HCl is going to react with other things in the molecule and protonate things we don't want protonated, right? And so that's our formation for the synthesis of amides. The reaction to form an ester with an acid chloride is going to look identical. Just put ethanol here, and it'll look identical all the way through to give you an ester, right? What I want to do is show you the mechanism for the Fischer esterification. Another very popular way to make esters, because again, we can make esters from an acid chloride or from a carboxylic acid, right? So if we have a carboxylic acid and we react that with ethanol in the presence of acid, and again, it's catalytic acid, we can form an ester. So whenever we have acid, as we've seen previously, we're first going to protonate the carbonyl. Protonate the carbonyl. Now the alcohol can act as a nucleophile to add. That's going to form our tetrahedral intermediate. And again, in a mechanism that is just like what we've seen before for acetal and ketal and those sorts of things. We're going to do a proton transfer. And now we can have water leave. So we now just have a protonated ester, and then to get to our final product, just deprotonate, and that gives us our ester product, plus we regenerate the acid catalyst. All right, so that's a Fischer esterification. Again, additional elimination of water. It looks very much like what we did for our acetal and ketal synthesis. Okay, so again, those are three of the mechanisms. Let me erase, and we'll go over the mechanisms for how you generate a carboxylic acid, starting from some of these other functional groups. So the most straightforward is reacting with an acid chloride. If we react that with hydroxide, we're going to form a tetrahedral intermediate. It has a leaving group on it, so we can just reform the carbonyl. Cl minus leaves. We get to our carboxylic acid, right? So very straightforward. If we have that same functional group with acid and water, we protonate the carbonyl first, as we'll always do with acid. Water can add. You can regenerate the acid catalyst straight away. Grab a proton off there. Now you can have the Cl minus leave. Right, and because you're in acid, it ends up being protonated, and again, you can remove that. Sorry about that. You can remove that and generate the carboxylic acid. Okay, so again, very straightforward doing that with acid chlorides. Right, so what would it look like if we had an ester? Right, so let's do the ester plus base. That's a very common way to hydrolyze esters. So if you just throw in hydroxide, right, and again it's usually hydroxide and water, right, what's going to happen? Add hydroxide, get a tetrahedral intermediate. And again, we're in base, so it's completely reasonable to have negatively charged intermediates, right? And so we can reform the carbonyl like we've done with esters before. And the negative charge ends up on our oxygen leaving group, right? And what will happen is that we'll end up deprotonating. So we'll get an alcohol plus a carboxylate anion. And then we're actually going to have to acid quench this to get to the carboxylic acid that we want. Because in base, carboxylic acid is going to be deprotonated because it's an acid. Okay, and doing that same reaction, basic conditions for an amide, it's going to look just the same. We're going to have nitrogen as a leaving group instead of oxygen, but it'll look exactly the same, right? We can do hydrolysis of this in acid. It's going to be the reverse of a Fischer esterification, right? And again, this is another place where the Fischer esterification is a reversible reaction. So depending on whether you have a lot of water or not, you can go one way or the other. So if you add a lot of water, you're going to get to the carboxylic acid, right? So acid and water, again, we're going to protonate. Water can add. Proton transfer. Reform the carbonyl. And then in the final step, regenerate the acid and get the product that you want. And again, the amide reactions will look just like these, right? But instead of having the oxygen leave, you'll have the nitrogen leave. And then the final mechanism is the mechanism of hydrolysis of a nitrile. And that was another video that we made separately. So you have that one as well. But again, hopefully you see these are all variations on a theme. I hope that as you practice through these and write through them, you're starting to recognize we're doing a lot of the same chemistry. And we're just practicing this idea of when we're in base, neutral and negative intermediates. When we're in acid, we're going to have positive and neutral intermediates. In acid, protonate the carbonyl first. In base, add to the carbonyl first. And then just work through with your curved arrows and get to the product that you know has to form. All right. And again, that's our summary of carboxylic acid derivatives. And now we can use that to make some interesting molecules and do some fun problems.